Very much. Good afternoon, everyone. The title of my talk, as mentioned by Madam Chair, is an asymmetric adaptive approach to enhance output power in kinetic-based microgenerators. This is the work of my PhD students who just graduated actually a few days ago. Thank you. Who just graduated a few days ago, Masoud, Roudneshin, and my collaborator from National Institute of Standards and Technology, Dr. Kamran, Sayrafian, and I'm Amir. This is the roadmap of my talk. I'll start with a brief introduction and some background on the problem that we will be presenting, and then the method that we will use to optimize, to maximize energy. And after that, I will present some simulations and finally conclusions. So energy harvesting, well, I'm sure you are familiar with different types of energy harvesters that harvest energy from existing sources and that are out there. And in particular, the ones that are that use motion to generate energy are very popular and becoming more popular, especially at the micro level, micro energy harvester level. And in particular, they are becoming more and more popular in wearable implants for medical applications, as many of you know. And among this class of microenergy harvesters, the ones that use static force, electrostatic force to hold the proof mass, as I will discuss in the next slide, they are very popular. So Coulomb force parametric generators that we are going to be focused on, and these are some different options that are out there for this type of devices. So for CFPG based microenergy harvester, we have two plates, lower and upper plate, the distance between them. But I'm not going to use too many equations, but just a few of them, and because of that I have some variables and parameters here. So distance between the two plates is 2ZL, and we have a proof mass which is sticks to one of the two plates because of the electrostatic force. Now, if you move this with a sufficiently large acceleration, hence force, it's going to move. This proof mass, small proof mass, is going to move from one plate towards the other one. Now, if this acceleration is large enough and persistent enough such that this proof mass reaches the other plate, then energy is going to be harvested. Otherwise, it's not. So only if the proof mass travels the distance between the two plates, it's going to harvest energy. And some of the parameters and variables that we will use in a couple of equations that I show. We have more equations in the paper, of course. So other than the distance between them, which is 2ZL, we have F, electrostatic force between the plates. We have Y, which is the motion with respect to the inertial frame, and Z, which is the motion, relative motion with respect to the motion of the proof mass, by the way, with respect to the body frame. So the objective is, of course, we want to maximize the generated power. This is the objective in any type of device like this, to harvest the maximum energy. But of course, there are many problems that need to be solved in order to achieve this maximization. And other than that, if you find maximum energy, which requires a lot of computations, that's not going to work because these computations are going to take some time, and in addition, some of the energy that you are harvesting will need to compensate for that. So energy efficiency, computational efficiency is very important here. So the equations that we have, I have just a couple of them here, three of them. So the first one relates the acceleration to the electrostatic force, and relay function is going to be +1 and -1 depending on the sign of this motion z going up or going down from the lower plate to the upper one, or the other way around. And the output is going to be, the output power is going to be F times velocity. F times velocity, and the harvested energy is going to be integral of this. So for integral of this, what we want to do, we want to divide these to small intervals of delta. So typically 1 second, 2 seconds in our experiments. And we want to use different values for F in each delta. So usually, typically, F is electrostatic force is constant, but we want to use we want to tune this electrostatic force in a way that, according to these equations, we get the maximum harvested energy. Now, think about the equations here. There is some there's a trade-off that we need to solve to balance things. So, on the one hand, if we want to you want this proof mass to move from one plate to the other one, we need to have an electrostatic force which is small enough so that this acceleration is going to overcome that and is going to make sure that the proof mass moves. But on the other hand, if electrostatic force is small, there's not going to be that much energy harvested. Actually, this equation 2 shows that. So it's part of the equation here in the power, harvested power and energy. So there is something, some balance that we need. This optimization need to solve. And one of the things that one of the important things that we do here to maximize energy is that when it comes to these intervals of delta, depending on whether the proof mass is at the lower plate or upper plate, we are going to use different policy for F. We are going to use different value for F. And this asymmetry is going to help actually to further maximize the harvested energy, as we will see in the simulation. So there are a couple of conditions here. First of all, when you look at the maximum absolute value of the acceleration in each direction, it has to be greater than the electrostatic force. So for sure, if the electrostatic force is greater than the maximum acceleration, this proof mass is not going to travel at all. And the other condition, as I mentioned earlier, is that to harvest energy, this proof mass has to travel that distance 2ZL between two plates. So the double integral that you see here has to be greater than 2Z, greater than or equal to 2ZL. This is a double integral of the acceleration, which gives position. So the optimization problem here is summarized in this equation here. We want to find two values for electrostatic force. One for the direction going from lower plate to the upper plate, and one from upper plate to lower plate. So we want to find these values. And for that, we look at the previous value of the waveform for the acceleration, and we have an algorithm in the paper, algorithm number 1, which first tries to detect whether or not, in which direction this proof mass is moving, from lower to upper plate or from upper to lower. Once this is determined, the algorithm looks at the previous interval and looks at the waveform, acceleration waveform from the previous interval, and uses a simple equation that you see here with the F margin that we use here to make sure that for sure the acceleration is enough to reach the other plate from lower to upper or the other way, and with that simple strategy, we see that we will have significant improvement, as I'll show in the simulation. So for the simulation, we use typical values for typical parameters: 1 gram for proof mass and the distance between two plates, 2 millimeters. This is more or less typical. And for electrostatic force, we use 11 different values and of discrete values: 0.5, 1, 2, 3, 4, up to 10. And the margin that we use to make sure that we are close enough to, we are not too far from the value that guarantees we reach the other plate, is 0.5 F margin. And the details are in the paper. So for the experiments, we use two scenarios. One scenario is an accelerometer attached to the leg while jogging, and the other one attached to the arm, making random moves. And of course, we followed the research ethics protocols of NIST and Concordia University to collect this information, this data. And in the next slide, we see the results that we get from the proposed method. What you see here is the acceleration waveform jogging when the accelerometer is next to the leg. The blue chart here is the maximum achievable energy, which is in fact obtained by kind of offline analysis, exhaustive search. Actually, we look at after the data is collected, we say, okay, if we have this data from the beginning, what would be the best values for the electrostatic force in each interval? So this is what we do. So this is impossible to get in practice because it's not. It's by looking at the entire waveform beforehand. And the one that you see here, which is close to the optimal one, is what we get from our proposed method, which uses asymmetry of the electrostatic force in two different directions and adjusts the values based on the last interval of the acceleration waveform. And we have two other results here based on the machine learning method that we have in an earlier paper, and also least squares method. Two other methods which performed well, by the way, but very proposed method is performing much better. And this is the other one, which is based on the random moves and the acceleration waveform is very random. And here again, the optimal values that we get from non-causal analysis, we're looking at the entire waveform, and then this was the waveform, this is the waveform, what would have been the best values results which were machine learning based and least square based, and not as good as the one from exhaustive search, of course. And very quickly, I can summarize this. So we proposed a maximization, energy maximization, harvested energy maximization technique based on well, looking at the waveform, previous values of the acceleration waveform, and using different electrostatic values for the electrostatic force in two different directions, going in from lower plate to upper and upper from lower, and dividing it to the time intervals of delta. And the method is computationally very efficient. Thank you very much.